Hi, today we are talking about the architecture enhancement in Apollo system. The Apollo system already has a complete architecture, but it still can be improved by adding some enhancements to the part of the system. This article provides new idea to improve the control and freedom of drivers in autonomous cars through a new feature called driver's mode. In addition to describing the impact and purpose of enhancement, the paper also provided a SAM analysis of the feature. At the same time, the plan for testing and potential risk of the feature and may occur are predicated. The new feature Drive Mode, which allows the driver to switch between automatic and manual driving via a button on the car when it's necessary. We use necessary constraint to deal with some special situation in order to make the function work as we planned. We will install 5 devices to help us in determining the constraint. This constraint operates independently but share information. Once it's detected that the driver doesn't satisfy any of the constraint, the system will switch to automatic and prohibit manual driving mode and make emergency course if necessary.
The proposed enhancement is defined as adding a new function of enhanced driver mode, which allows users to automatically switch between manual driving to automatic with the testing of tire detection, body condition monitoring, and emotion detection. Although currently Apollo system allows users switch modes manually, the point is in order to let the system engaging in daily life. The occasion of when to perform the switching is one of the big concerns. Therefore, we introduce this enhancement intention with the aim of benefiting the driver safety and the practical of the system in reality.
The functional safety subsystem is a system that will do fault detection and troubleshooting according to the situation when the driver is exposed to safety risk due to unexpected conditions. But most of the functional safety subsystem only focus on hardware and software issues. We can add better health detection features mentioned in this paper to the existing subsystems. For example, if the driver suffers an outbreak while driving in a manual driving mode, the heart rate monitor on the seat will immediately provide feedback to functional safety subsystem based on the collected heart rate data, and the system will troubleshoot the situation accordingly. And the existing Apollo heuristic detection engine is based on the context-aware detection technology to detect abnormal behavior. So adding additional enhancement can help us combine the existing engine to obtain more complete information about the driver's behavior and interact with our other systems to determine whether the driver is in a state of abnormal behavior, such as drunkenness, fatigue, or reckless behavior.
The enhancement is mainly related to 4 subsystems, which are perception, monitoring, HMI, and control respectively. Most work of algorithm and the monitoring of the drivers in the vehicle is done by perception. Control is responsible for data transfer, and HMI is used to ask the user whether to enable the enhanced mode. Only little addition takes place in monitoring subsystem to monitor some new objects, which are the hardware and the software algorithm added due to the enhancement.
The effect of enhancement could be divided into 6 parts. For maintainability, the maintenance fee of Apollo system will increase. Secondly, enhancement will bring positive effect for availability, since the drive mode is less likely to be replaced. Thirdly, the enhancement of adding a new driver mode may add difficulties for testability, since it will hurt testers' physical and mental aspects. For performance, the enhancement is positive to this part, since it remedies the main defects of self-driving cars. For conceptual high-level architecture, as shown by the yellow box in Figure 3, it adds driver well-being detection for camera and adds a new device, microphone, with the same function. For concrete high-level architecture, it remains the same compared to the previous version mentioned in A2. For conceptual low-level architecture, as shown by the yellow box in Figure 5, microphone and 2 types of camera as function of driver well-being components. For concrete low-level architecture, as shown by the yellow box and arrows in Figure 6, microphone and heart rate monitor are added, which depends on inference and common that is used to detect drivers' physical and mental conditions.
The first use case is quite simple, which basically illustrates the launching of the enhanced mode. So the user turns on the mode from the user interface and invoke the mode to control. Control module returns the message back to the HMI and call perception to launch the predict work. The second user hit shows how the switching between 2 driving modes performed. Once the perception module concludes the negative driver status is present, the switching signal is passed to the control module. The control will send a message to the user interface and also send a signal to perception and CAN bus to allow normal perception starting and enable the Apollo system to take the command of the vehicle.
As for the SAAM analysis, there are three main stakeholders in the proposed enhancement: the drivers, developers, and the investors. The first approach turns the vehicle into self-driving mode immediately after the system detects unusual actions of the driver. If there is any evidence that the driver is experiencing an emergency illness or has a fluctuation in their emotions, the car will switch to autonomous driving immediately. The second approach waits for a response from the driver. If the driver responds to the signal, which means that he or she is fine, then the vehicle will not switch modes. Otherwise, the vehicle will switch to autonomous driving. Here are two tables for the SAAM analysis, and it shows how the two suggest ways to realize our enhancement impact, each identified NFR and its stakeholder. The advantages of the first method are that the system can detect and switch driving modes automatically, which has fast response time. The safeness of the driving experience is guaranteed to a great extent. As for disadvantages, the first method cannot guarantee that the detectors will analyze and make the right judgment every time, which lowers the system's accuracy. The pros of the second way are that the reliability of the system is improved compared to the first method. The driver's response allows the system to generate more accurate results. As for cons, the driver himself or herself has to respond and operate the mode, which increases response time and might distract the driver. From the SAAM analysis, we can see that the approach 1 is the overall best one, as it has high performance, usability, maintainability, and reusability. It also satisfies all the requirements made in our proposed enhancement. Although the second approach has higher reliability, it still needs to implement almost all the features in approach 1 and an additional feature, which makes the implementation more complex. Therefore, approach 1 is the overall best one.
As mentioned in the previous part of this report, HMI perception monitoring and control subsystem will be impacted. Firstly, HMI will add functions of showing negative status of driver's well-being. Secondly, the perception will be able to receive negative signal gathered from cameras, microphones, and heart rate monitors. Thirdly, the monitor module will be used for detecting if failure of automatic switching is taking place. Finally, the control module is used to launch the mode when the driver selects the mode from the user interface driving.
For testing the impact of interaction between the enhancement and other features, we can use the dummy with the simulated heartbeat device. The device can address the heartbeat rate at any time through the remote device to assume the driver who may have a heart attack while driving. This simulation can help test whether the heart rate monitor can transmit the data to the functional safety system on time, and whether the car can switch from manual to automatic driving mode immediately. Similarly, we can simulate fatigue, drunkenness, and reckless behavior by having dummies that are able to represent human expression and physical behavior. We can let the dummy simulate fatigue and reckless driving through specific behaviors to detect whether the enhancement can cooperate well with Apollo's heuristic detection engine to ensure that the interaction of the system can be carried out in any situation, achieving the purpose of protecting the personal safety of the driver.
The potential risk could be divided into the following three aspects. For security, in case 1, when one of those three key devices mentioned above is inefficient, the Apollo system will not detect the driver's discomfort. Thus, the driver mode will not be trained to automatic driving mode, which could not ensure the driver's safety. In case 2, if the automatic driving mode is out of control after detecting driver's discomfort, the safety of the driver still could not be ensured. For maintainability, those three devices are assembled within the driver's action zone, which means it is easy for the user to hit those devices, which may lead to device damage. For testability, it has potential risk for testers in both physical and mental aspects.
In summary, the enhancement can be added to the overall architecture only based on assumptions. We need to consider the compatibility and interactivity between the existing system and guarantee that use case and impact of the enhancement according to the current state of the system. Meanwhile, we must ensure that this function is testable and the risk is within the acceptable range in order to make sure that this enhancement can be used perfectly and safely in dealing with different situations. Thanks for listening.